Let's get started with Beam UDL calculator for Tekla Structures by double-clicking on the TSCP package or Tekla Structures extension package. This will then open up the extension manager, and you can select which versions that you have installed on your computer of Tekla Structures that you'd like this extension to be installed into. I'm going to go ahead and select the current version of Tekla Structures. I'll press the import button, and then it will show that it is queued then for import. Now when I press the close button, you'll see that there's an option for yes or no. If you don't want to delete the original file, like if you have this file on a server for other people to install, then you'll say no. If it's just you downloading and installing this and you want to remove this temporary file, you can say yes, and then that file will go away. Next, let's go ahead and launch up Tekla Structures, and here we'll see a splash screen that'll show us that this extension is being installed. Now once you're in Tekla Structures, you'll come over to the Applications and Components panel on the right hand side of the screen. You'll then see a CMK BIM group, and then you'll see the Beam UDL tool. If you double click on it, it's going to open up that tool. Now when you first open it up, it's going to open up the trial and the licensing dialog box. If you're just doing a trial, you can fill in your information here and press the trial button, and it'll allow you to use the tool up to 10 times before you have to purchase. If you've already purchased the tool, then basically you can email us here at cmkbimconsulting@gmail.com this license code, or you can go ahead and press the request license button. This will then send us an email and we'll reply with the license that you'll paste in here. Once you've received your key, you'll just paste it in the license and then you'll go ahead and say register. If you see a successful registration notification and you'll also get an email, then everything has been correctly done and you're able to press close, and now you can use the tool. Now when the tool first appears, there's some important disclaimer information that you need to read. It tells you about the limitations of the tool, as well as that you are fully responsible for verifying all the end reactions that are calculated based on the pieces in the model, and then the AISC tables that has the shape library from AISC's website. And again, I'll show you a little bit more about that here in a second. Now, the pieces that this is limited to are basically W-flange shapes, and again, this is meant for the imperial environment, using imperial measurements and mainly with the USA profile catalog and USA imperial environment. It's not tested or meant for any other environments or even Canadian shapes. All the input values and calculations are all based on KIPS, and then also imperial measurements from the shapes database. So that's the first thing to kind of talk about. Then as far as the types of pieces that this is limited to, it's limited to wide flange shapes, rectangular HSS sections, and then also channels. And miscellaneous channels are excluded from that. It's just looking at C shapes. These are the most common shapes that are utilized in a beam framing capacity, which is what this tool is mainly used for. It is for calculating the end reactions based on a uniform distributive load or maximum shear on the pieces in like a beam framing, which you would then utilize in your auto connection and auto defaults or in your connection design. So essentially I've got a few different beam sizes in here. So I've got just a simple 18 by 35, got a very short W21 by 44, which is going to give us a good maximum shear calculation versus UDL because the beam is short and it's a fairly large profile size. Got a rectangular tube here, a channel, and then just another beam size here that's a little bit longer. Now what we're going to next go through is that the material grades also matter. That's why this is very specific to the US Imperial environment. Basically for the FY value, I'm looking at A992, I'm looking at the A1085 material grade on tubes, or A500 grade B or grade C, and it will look at those values based on those grids for the FY value in the calculation. And then also A36 is considered here, and I do know that channels are more and more moving over to A992 instead of A36 now. So the values for the FY are based on the actual string of the material grade that you use on the pieces. So that's also described inside of here. Now, if there's any pieces in the model that have moment designated at the end, so if I go to user-defined attributes here, we go to end conditions. If an end is specified at moment yes, then the shear and the UDL will not be calculated for this because it's assuming the engineer has given you the shear, the shear and moment reaction and everything that's required at the end of that member. And so if this end is set, or any of the ends is set to yes, it will not put this value on there. So that's something also to watch out for. And then there's a file that this depends on, which is essentially found inside of the model folder. So when you first launch this tool inside of this particular model, what it does is inside of the model folder, so if we go into there, there is an AISC shapes.csv file that has been created. And so I'm going to close the tool down here for a second, and if I just open this up, this will open up Excel, and you can see that this CSV is a comma delimited file. But what I did is I essentially pulled only the wide flange, channel, and HSS shapes from the AISC Excel spreadsheet that you can get on their website. And then I also got rid of all of the columns of data that don't matter and only left the columns of data that matter for the maximum shear and UDL calculations that we need to use. So I do not depend on Tekla Structures at all for any of the values in the calculation other than the work point length here. So like I calculate the length based on the distance from the start and end point, or the yellow and magenta point, and then I of course look at the profile and then the material grade, but then all of the other shape data and information is actually coming from this this comma delimited file here, because it's design based information rather than detailed numbers, which is often inside of Tekla Structures. So again, this is just showing you that this is another file that needs to be here. Now I got this off of the AISC website, and I do reference where I get this from inside of the tool. So if I come back in here, open up Beam UDL, you'll see that there is a website here that is referenced, and this references you to the Excel spreadsheet for the AISC 15th edition manual. And it's an Excel spreadsheet that has all these, and that's how I've derived this. If you need to create a 14th edition or earlier, then you can use the historical shapes database, or you can use one of those older Excel spreadsheets and just modify it to make the CSV file very similar in format and structure to what I did here with the 15th edition. So those are some of the disclaimers and things that you just kind of need to read and understand before you actually leverage the tool. So now let's go ahead and get something actually set here. Now, when I click on a beam and I go to the user-defined attributes here, on the end conditions tab, this is where we're going to be writing the data. And so really all we're focusing on is calculating the shear reaction value that we want our connection to be able to resist and meet. And oftentimes on jobs, you'll see the structural engineer has designated they want 50% UDL, or a percentage of UDL, or maximum shear, whichever governs, and then you're supposed to be designing your connections to meet that. So what we'll do is we're going to basically select the pieces in the model that we want to calculate this UDL for. Now, if we don't select any pieces in the model, then what it's going to do is the tool will scan through all of the beam type parts in the model. It'll ignore poly beams, it'll ignore columns that are perfectly vertical, it'll ignore plates and things like that, unless they're beams, but it ignores those profile types, right? So it only looks for channels, rectangular tubes, and W-flange shapes. And then basically what it'll do is it'll scan through all those selected, or if nothing selected, all those beams in the model that match that criteria, and set the reaction for this. So let's go ahead and go through the criteria real quick. The very first thing we want to set is what AISC code are we working with here. Are we doing ASD or LRFD based? And then the next thing is, are we doing a composite or non-composite floor or beam? Now, oftentimes, if you're just doing non-composite, then the engineer will specify 50% UDL, and then basically it just it calculates that reaction. Now, if you have a composite floor system, then sometimes the beam actually becomes stronger because of a deeper cross-section area there with the slab and the beam combined together, so you get potentially stronger. The beam can be worth more, be stronger, and so sometimes you'll see a factor of increase here for designing to a composite, like shear connection instead of non-composite just with the beam. Then the other thing here is you'll sometimes see that the engineer wants a connection designed to like a certain minimum kip reaction value. And so if the UDL is less than that minimum kips, then the minimum kips will be used. And then the last thing is some people don't want maximum shear to be considered, so it is an option. You can check or uncheck that. And what that means is that if you have a really short beam here, the actual UDL calculation, the bending moment there that's calculated, is much larger than what would be the actual maximum shear that this beam and the web could handle. And so really one governs over the other. So usually this happens when you have short beams. A maximum shear is going to be the limit state more than like the actual UDL, and so that's why I have this as an option here. And again, if you don't want that to be chosen, then you can do that either way, one or the other. Okay, so now that we've got gone through kind of those different states and those different design criteria, all we really need to do here is go ahead and say calculate. That'll then go through the whole model since we didn't have anything selected, and it'll tell you once the progress is done. So here it says end reactions applied. And again, if we click on a beam and we right click and say user defined attributes, go to end conditions, we'll see the reaction there. Now, the other way that we can kind of see this is if we actually come in here and if we specify, if we right click and inquire part, we'll see here that if we scroll down to the more section, that we'll see the actual shear values that are associated to this piece. Then there's a Beam UDL formula, user defined attribute, and Beam UDL criteria. This basically just says what were the inputs and the formulas and the numbers that came up with this actual reaction that we see here. And so you can then use that as a way to just cross-reference and see if this matches the way that you would calculate it or the lookup table in the AISC manual. Now, the other thing you can do is if you want to quickly spot check this against a manual, you can just come in here and you can say export. And what this allows you to do is you can just export this file. And again, it's just a comma delimited file. It'll then open up in Excel, and then you can see those particular shapes. You'll see the profile, the length, which again is the point-to-point length. And if you just quickly come in here, select all these columns, auto fit the column width. You can then see also the design criteria, user defined attribute, and the equation that was used to come up with the specific reaction. And then there we go. Now, if the minimum kips was actually used, what it'll do is it'll show the UDL formula, which was 12.7 kips, but the minimum kips in the dialog box was 14, so it actually put 14 kips here, and then it just puts that as part of the design criteria. If maximum shear was used versus UDL, it'll put that formula in there, and it'll show it here in the design criteria that that's what was leveraged and used for this particular calculation. Now, what we can also do is we can come in here and we can select the pieces that we want to clear all of the reactions from. So if you want to start all over and change some of the criteria, you can. Now, one important thing here to understand is that if you press the clear button and nothing is selected, it's actually going to give you a warning message, hey, nothing was selected, please pick pieces and try again. And the reason for that is because sometimes you may need to manually input reactions or loads, or there's something in the model, and I don't want you to accidentally blanket just get rid of reactions and things from other stuff that you've manually modified or put in. I want you to very carefully decide whether or not you want to clear all the reactions and codes. So when you press the clear button based on the selection, it will clear that. And then again, if we come in here and we inquire on that part and scroll down, we'll see that there's nothing here for those user-defined attributes under the more. And again, if we click on a beam here and go to user-defined attributes, we'll see on the end conditions tab that all of those values have now been removed. All right, so that's the basics of using the Beam UDL tool here by CMK BIM Consulting for Tekla Structures.